if knocked out, it's a phosphatase. And here we have in parallel the oncogenic kinase, the PI3 kinase, which is also mutated and hyperactivated, for example, in colon cancer and many cancers. And probably this signaling pathway is the most often activated cancer pathway in human cells. And we have here not only PI3 kinase, it's as kind of the driver, the most upstream molecule, normally counterbalanced by the PTEN phosphatase. But then we have in addition also the AKT molecule. And recent literature has shown, publication in Cell a couple of weeks ago, that also AKT is a clinically relevant oncogene because we find in a subset of colon tumors also this molecule to be mutated. So there is a really strong evidence that this pathway is crucial and critical for the malignant transformation and the growth and progression of tumors. Not enough with that. We have here, again, another tumor suppressor gene, the tuberous sclerosis gene, which, if mutated, cause a tuberous sclerosis, so hyperproliferation syndrome. And we have here then the mTOR, the mammalian target of rapamycin, also again in the same pathway, which has been addressed as target, and recently the first drug has been approved. So it is very obvious that this is a very important cascade signaling. And just as an overview, and then I do not bother you anymore with that slide, at least not for the moment, you see that there are numerous efforts in order to address this mechanism in this pathway. And here we have PI3 kinase inhibitors, and there are by now several more. This is a review from 2007, but I can tell you there are many more companies now pursuing this approach. We have rapamycin analogs that target the mTOR, which I showed to you, and actually temsirolimus has been approved in renal cell cancer last year, as I showed you briefly on one of the previous slides. And there are other compounds ahead or behind. And then we have this MAP kinase pathway, and there we have two front runners. The one is the sorafenib or Nexavar, which is already approved in renal cell cancer, and last year was also approved, but not included because I think happened too late, for liver cell, hepatocellular cancer. And I think there the phase 3 results that were presented at ASCO last year were really impressive because for the first time in over 30 years, an agent has shown efficacy in hepatocellular cancer, which has been believed to be more or less chemo-resistant. And now we know it is not. We just have to understand and attack the right pathways. And this, besides being a VEGF receptor inhibitor, which is the predominant activity, also has activity against the RAF kinase. And then there is a compound, actually there are 3 in clinical trials that target one step further downstream, and this is the MEK kinase. And unfortunately, I think this compound is no longer in development, but others are. So we see there are a lot of efforts, and hopefully over the next couple of years, there will be more molecules than being clinically tested, and hopefully then added to the arsenal of physicians in order to treat those diseases. Very short mentioning just of other pathways, which I will not go into. Hypoxia is a very important part, especially also in head and neck cancer, because it is in close correlation with sensitivity to radiation therapy. And there is one very important molecule. This is the hypoxia-induced factor 1 or 2, which is induced. And then, of course, at least since Professor Strebhardt is also here, I cannot go over this presentation without mentioning at least the cell cycle. So, of course, mitotic regulators, and I've told you in the beginning that docetaxel, has been approved for the treatment, but there are many more agents now in clinical development, specifically targeting then mitotic regulators like PLK, Aurora, or the kinesins on that part. But this is more for the discussion. And then, on the first summary, I would say numerous pharmacological inhibitors against critical cancer targets and pathways are currently developed and hopefully will improve the treatment options in the future. However, as already seen with the resistance development towards Iressa and Tarceva, based on the genetic instability and heterogeneity, tumors consistently adapt to the environment and may develop resistance against many of those treatments. And therefore, it really is crucial that we understand the critical oncogenic pathways, and this is sometimes called either oncogenic addiction or oncogenic shock, mechanism that we really identify those pathways where the tumor can actually not escape from. Now coming to the second point about targeted application. When we look and say why can't we treat cancer even more effective today? Then of course the point is it simply that we need better and more targeted cancer drugs? Is it just that we need more affinity, more selective drugs and then it would be easy? And actually I don't think this is sufficient. And I just took a little bit provocatively here this Magic Cancer Bullet. There's a book written, or at least written under the name of Daniel Vasella from Novartis. Everybody would agree that Gleevec is the gold standard for a targeted drug. However, if we look at the molecule itself, it's by no means particularly selective. It inhibits a lot of cellular kinases. And that's the reason why it's now being often used kind of in other indications, approved or unapproved, because it has many activities. But it's not really the best and most targeted compound. But what really makes it outstanding is the targeted application of Gleevec to select it in actually very small tumor indications that critically depend on the inhibited kinase. And they started out with CML, where really I think the stunning effect of then sending 95 or even more % of the patients into remission was observed first. But then you look, gastrointestinal stroma tumors have been basically not really on the landscape before Gleevec was there, because nobody thought of it. But it has one target that is addressed by this molecule. And the same hypereosinophilia syndrome, even a more specific indication, myeloproliferative disease. But again, it is just to know where to apply a targeted drug that really makes a success out of that. And therefore, it's the targeted application of a targeted drug that defines success in oncology. What do I mean with targeted application? I mean, we have to understand the molecular and pathophysiological context under which blockade of a given target by the targeted drug results in the maximum therapeutic effect. And this is kind of close to the subway network and subway map of New York. But what you can see, these are actually oncogenic pathways. And the concept, I think, is easily comprehensible by just realizing that it doesn't matter necessarily whether you really hit one or the other target, but the question is there any way around? So I can inhibit here MAP kinase pathway, and then I think, okay, I can actually very effectively block this pathway. But if there is here basically a detour, then maybe some tumors or maybe many tumors can basically circumvent being dependent on that and just kind of come to replication or cell cycle proliferation just by another pathway. And therefore we have to take this into consideration. And just to show you that this is not only in an animated cartoon, but also in real life, this is again the PI3 kinase pathway. And I will spare you from going into the details unless you urge me to. But what you can see, this is not the typical top to bottom pathway in a singular direction. But you see here how many feedback loops are here involved and how many crosstalk is here actually involved. And this is also for the clinical development very important, because, for example, in the early development of the mTOR inhibitor, tensirolimus, people would be stunned because they actually would sometimes saw a worsening of the disease, because by blocking one pathway, they would get actually via feedback loops increased signal transduction via another pathway. And you have to understand that in order then to be able to select the right patients and do good for them. Does that play a role in clinical cancers? Yes. Just look at non-small cell lung cancer. And here now we already take the adenocarcinoma. So no longer the broad types of all. This is these are adenocarcinomas of the lung, which you clinically and pathologically would be very difficult to distinguish just kind of by IHC. But depending on whether it occurs in a never smoker or in a smoker, we typically have a clearly difference in the molecular response pattern. They both express the EGFR receptor. That's fine. So you may say this is a good target. But whereas if you have the tumor arising from a never smoker, you typically have this as the predominant signal transduction, the PI3-AKT pathway, and then dependent on the EGFR receptor, the RAS-RAF pathway, which I have shown you before. In smokers, you very often have mutated RAS. That means this tumor and this signaling cascade does no longer depend on the EGFR receptor. So therefore, the EGFR receptor as a target will not be effective or much less effective in those tumors, because simply downstream there's a different pathway at first sight which already is active and therefore not susceptible to inhibition. Now, this is something where many people would agree that this is relevant for small molecule inhibitors, which typically depend on the signal transduction. However, a couple of weeks ago, it has been shown for antibodies as well, for the first time. So here is Vectibix, and this is another EGFR antibody from Amgen, very similar to the Erbitux. Not being offending to any one of the companies, but basically very similar. And you would have said beforehand, it just matters how much EGFR receptor is on the surface of the cell, whether it is a good target and can be treated or not. And the first results, especially coming from colorectal cancer, showed that there is no correlation, no direct correlation, between the level of EGFR expression, at least by immunohistochemistry on the tumor cell, and the response of the tumor to such a treatment. But now, even one step further, it has been shown that this antibody depends in its activity again on the status of the Kirsten-Ras gene. You know that Kirsten-Ras is the most often activated, or one of the most often activated oncogenes in colorectal cancer. And what has been shown here is that basically this treatment is less or not effective in those tumors who have the RAS pathway. If we just go one step back, this is the same mechanism. If this RAS gene is activated, then an antibody interfering here has no effect. And this is now also clinically been shown, and therefore in the EU, the EMA has granted approval for this drug only on the basis that it's used for the treatment of colorectal metastatic cancer that has a non-mutated RAS gene. And this shows this predictive medicine to be highly relevant. I think in the future we hopefully will see more of that. But what is the prerequisite for that? The Cleveland example demonstrates that the targeted drug needs to be applied to the right cancer subtype or even to the right individual cancer in order to be effective. Ideally, molecular markers predicting the efficacy of targeted drugs can be established from the drug target itself. So ideally it would be just looking, is the EGFR receptor there or is PI3 kinase there or not? That's straightforward. However, in many cases, those predictive markers are different from the actual drug target, and therefore we have to understand the cellular context within this cancer. And finding and validating those predictive markers for the targeted application of targeted drugs is a major challenge that requires the close interaction between basic, applied, and clinical researchers for the benefit of cancer patients. And with that, I hope to have shown you that it's the targeted drugs and the targeted application that is required for therapeutic success. And with that, I will thank you for your attention. I hope it didn't bother you too much, and I'm looking forward then to questions and discussion. Thank you.